Hello, welcome to this video on discrete time versus digital. The concept of digital signal processing, the words discrete time and digital often are used interchangeably and they mean something very close, but there is a subtle difference. And the purpose of this video is to clarify the difference between these two terms. What is a discrete time signal? So any sequence, integer indexed sequence, is a discrete time signal. So the discrete time signal time does not take all real values. That is, if you observe over here, xn, this n can take only integer values such as -3, -2, -1 and so on. The xn itself can take any real or complex values. For example, it can be 1.3, it can be pi, it can be 4/7, any of those. Since the n, that is the time index, is restricted to be only integer values, we call it a discrete time signal. So any real or complex sequence can thus be called a discrete time signal. If you look at this example, we use the stem notation or the lollipop notation to represent the signal. The discrete time signal for n is equal to 0 is 1.2, for n is equal to 1 is about 2.3, for n is equal to 2 it's about I think 3.6, and for n is equal to 3 it's just below 3. Notice that the values are defined only at integer values of n, and in between the value is, it's not defined, meaning the sequence xn is defined only for integer values of n. So it is not appropriate for us to ask what is the value of x of 0.5 or something of the sort. No, it is defined only for integer values of n. It's unspecified for any other values. So when we talk about digital signals now, notice that we are now using the word digital. We bring in the concept of quantization. Quantization refers to the restriction of the values which the signal can take. Over here, we represent the digital signal using the blue stem dots. For example, xn when quantized becomes 1, let's say at 0, and at 1 it was slightly above 2, it got rounded down, so it's rounded down, and here it got rounded up and got rounded up slightly. Why? We restricted the set of values which xn can take to only integer values, which are 0, 1, 2, 3, 4. What effect does this have? This actually changes the signal, meaning the xn which you obtain after rounding the values is not the same as the xn which was present earlier. Does this have any impact on practical situations? Well, you can say that if the rounding is not significant, then let's say it's a speech signal, for example, then if you round it off by a little bit, maybe if you hear it, you will continue to hear the same thing. But in some applications, even the slightest change can lead to issues. So why do we need to perform this restriction of the values which xn can take? The reason is because computers and digital signal processors, which are specific processors used to perform digital signal processing applications, they typically have finite precision, meaning that they can hold only finite precision numbers and not arbitrary precision. For example, if you have an 8-bit DSP, it can hold only 256 values in its memory locations and registers. So, for example, you can only store the values -128, -127 and so on up to 126 or 127, which are 256 values. Or if the scaling is not sufficient, you can then represent them as -12.8, -12.7, up to 12.6, 12.7. So this is all you can do. Of course, modern DSPs do have the capability to perform floating point operations, but that comes at additional cost and complexity and is best avoided when you need high-speed applications. Why is this preferred? That is because integer arithmetic is fast and often it is sufficiently accurate to perform the signal processing operations that you need, and floating point operations are not needed. But there are a host of issues because this rounding can cause changes, and then performing computation on these changed signals can lead to errors as well as some overflows and some incorrect results that can come in and spoil your system. This is something which we will not see right now, but we will try to look at this as we go back to the end of the course. So just to give you a perspective, let us say that this digital signal, rather this discrete time signal, came by only restricting the values of n from a continuous time signal. By quantizing xn, notice that the values which xn takes are also now limited. So this quantization is what leads to a digital signal as opposed to what was just a discrete time signal. This is a discrete time signal, it became a digital signal. To summarize, discrete time emphasizes that the time is discretized, while digital implies that the values that the signal takes are also limited to a discrete set of values. Now, use of digital implementation, like I mentioned, it's a practical requirement, but there are interesting challenges and you have to handle them carefully depending on your application. But we will look at all those only towards the end of the course. For the rest of the course, we may use these terms interchangeably. So when I say digital signal, I actually mean discrete time. And whenever there is any change in that notation, I will alert you. Thank you.